Hello and welcome to Lecture 15. Here we're going to cover the topic of motion with drag forces. This is the last section in Chapter 6, and it is applying Newton's laws to specific situations, and that's what we're doing here. We're going to apply it to the specific situation of drag that has one interesting facet with a lot of consequences. All right, so let's define some types of drag, and then let me kind of reveal what it is that's different and interesting about drag, okay? So, there's two types of drag. Their technical terms are Stokes drag and Newtonian drag. All right, and what separates them is Stokes drag applies to anything that is small or moves at small velocity. That's what the small v represents. And Newtonian drag applies to macroscopic objects like a skydiver that are large and moving at large velocity. The technical differentiation between them is something called the Reynolds number, but we don't cover it in this class. Okay. All right, so let's define Stokes drag. So it's drag for small and or slow things. So like, raindrops is the example I have. Things sinking in fluids because they tend to fall much more slowly. Certainly anything like aerosols or bacteria. Okay, so this drag force is proportional to velocity. Okay, so we'll come to that when we talk about the math side down in the key equations. But for now, it's a force that's proportional to velocity. All right, although it is only truly applies to smaller slow objects, we may use it elsewhere due to the fact that we can actually solve it analytically. So we can't really do much of Newtonian drag. Its mathematics are beyond the scope of the class. There actually still are analytical solutions, unlike a lot of things in physics, but they're just a little bit too complex. They use a lot of hyperbolic functions, like cosh and sinh, if you've seen those in math classes. Okay, all right, so what is Newtonian drag? So it's drag for large and or fast things. In this case, the drag force is proportional to the square of velocity, okay? And it's very complex mathematically, so we'll not use it much. So we're only going to use basically terminal velocity for Newtonian drag. It's the only time we're going to see it, all right? And let's define that. Terminal speed, also called terminal velocity, but speed sometimes is more of an accurate name for it because we usually care about its magnitude, not its direction, because we know it's pointing down because it's talking about things that are falling. But terminal speed, it is the speed reached by falling objects after a long fall. So when they're falling for sufficient amounts of time, they reach terminal speed. All right, what is it? Well, the idea is this. Since drag force grows with velocity, see, there we're really kind of starting to touch on the significance of the statement, proportional to velocity. Well, that force, that drag force, eventually grows large enough to match gravitational force, because gravitational force is constant. At least we're assuming it's constant, and that's a good assumption. And when this happens at equilibrium, an equilibrium is reached, which means zero acceleration by definition. All right, equilibrium means net force equals zero. Okay, so that is the condition for terminal speed. Okay, and this speed at equilibrium is called terminal speed. All right, so there we have the crux of the matter, the thing that makes drag so different from friction, because they're both types of forces that slow things down. They always oppose motion. We'll see when we talk about energy that they are both non-conservative forces, okay? But what really separates them, which makes them so much different to deal with, is that drag has that one little rule that it's either proportional to velocity or proportional to the square of velocity. So it doesn't just remain constant, it increases as your speed increases. But how do you quantify that? Well, let's see, okay? So here is the definition of the drag force. Now this would be the Stokes drag. This is the only one that we're going to work with in any significant way. This is the only one we're going to discuss acceleration and displacement and even time-dependent velocity. It's all going to be for Stokes drag. And this is the form of Stokes drag. The negative because it opposes motion. It's always going to point in the opposite direction of velocity, so that's what the negative represents here. Think like Hooke's law, all right? And furthermore, it has a simple form. It's B times V. Well, what's B and what's V? B is the drag coefficient. It has units of kilograms per second, all right? So mass per time. It's just how draggy this situation is. It is derived from a combination of the fluid properties that are creating the drag in the first place, the shape of the object, and so on. We'll see when we talk about Newtonian drag that we actually split up the drag coefficient into kind of its specific constituents, the things that really form it. But when we talk about Stokes drag, we don't do that. There's a number of reasons. Shape is less important for Stokes drag, but not to get into the weeds and go off on a tangent. The point is that for Stokes drag, it's a single coefficient. All right, and it's usually given, or maybe that's what you're solving for. And then what is v? Well, v is velocity. Okay? So here we have a force. We've seen that before. We've seen certainly Newton's second law, F equals ma. And then we've seen things like, the friction force, which is defined as some coefficient, right? So that, yeah, some coefficient, right? In that case, just times the normal force, so times another force. But here we have a force times a velocity. First of all, that means the coefficient must have units, right? Which I always specified, kilograms per second. But second of all, that means that the force is inherently non-constant. Now, we've dealt with non-constant forces before, because non-constant force just means non-constant acceleration. We certainly have the mathematical chops to do that. But they've always been polynomials, haven't they? Right? It's always been, acceleration is changing as a function of t to the fourth or something, or the square root of t, whatever it may be, okay? But we'll see that this is a different beast, okay? It's fascinating and elegant, but what does it look like? Well, let's do a quick little derivation once we define a couple more terms, all right? So first of all, here's terminal velocity, f sub t, all right? And then this is just mass times gravity over the drag coefficient, which we already talked about. And then, but we can also call terminal velocity gravity times this letter here. By the way, this is the Greek letter tau, and that's the time constant. It's just a convenience for expressing our other equations. And what we can see that it's either terminal velocity divided by gravity, or it's m over b. It's mass over drag coefficient. That's all it is, okay? It has units of seconds, all right? It is a time, and it kind of represents like how long it takes for, not for the object with drag to get to terminal speed, because we'll see that that takes forever. It literally never truly reaches terminal speed. It asymptotically approaches it. But it tells you how long it takes to kind of get close to terminal speed. The time constant is a value that really tells you, is this an object, if it's large, is this an object that's taking a long time to speed up? Or if the time constant is maybe less than a second, that's telling us this is an object that speeds up very quickly and reaches a steady state, so something close to, at least close to equilibrium in very little time. Okay, so the time constant does tell us a bit of a story, but again, it's a time, and it also is just a convenience, as I said, because we'll see it shows up in the equations. Okay, so what are the equations? Okay, well, here they are, all right? This is the force, right, which everything stems from. This is the definition. Everything is a consequence of this definition, okay? A force that is proportional to velocity. We've never seen that, okay? But what does that mean? Well, that means that the acceleration decays exponentially, right? So right now, just take my word for it, but I'll show you in just a minute. So the fact that the force is proportional to velocity, that means that the acceleration decays. Now that makes intuitive sense. Because if you think of an object with drag, the skydiver being a wonderful example, the moment the skydiver jumps out of the plane, at that first moment, their gravitational acceleration is g, because they're in free fall. But from that moment on, their acceleration, their downward acceleration, is going to become less and less. It's going to be smaller and smaller than its initial value of gravitational acceleration. Because eventually they're going to reach their equilibrium. They're going to reach terminal velocity, at which point their acceleration is what? 0, of course. So that means that they've been gradually accelerating less and less and less. They were still accelerating the whole time, so they were still speeding up the whole time, but they were approaching that final equilibrium. So their acceleration decays. It doesn't decay to 0, instead it decays to g. Because if we look at this, especially here with a coefficient over a mass, maybe that's a little cluttered as in terms of the exponent on the transcendental number e. But once we actually look at it, once we have the time constant in there, we can really clearly see that what this means, that as t approaches infinity, e to the negative t over tau approaches 1. And as it approaches 1, that means that acceleration in the y direction approaches g in magnitude, and it's going to point down, okay? So that's the idea. It's acceleration decaying until it eventually gets to, until it eventually gets to 0. So I misspoke, and I was thinking of something else. Now, exponential decay, of course, means it actually decays to 0. If you probably were screaming at the screen right now, being like, "That's not true. Exponential decay doesn't just decay to 1." So sorry for having multiple ideas in my head at once. So this, of course, does decay to 0. Okay, it decays to 0 as t approaches infinity. Okay, just as t gets big, it doesn't have to get huge, right? But as t gets large, this exponential decay, depending on how large the time constant is going to get really, really small. And that means that this is going to approach 0. Acceleration will approach 0 because, of course, it has to, because I already said terminal velocity is once equilibrium is reached, and that's when net force equals 0, and acceleration has to be 0, right? By definition, Newton's second law. Now, the approaching g business is actually when t is 0. Because when you have e to the t over tau, so e to the t over tau, for t equals 0, e to the t over tau would just then be e to the negative 0, would just be 1. So that's going to tell you that at the initial time, the initial acceleration is g. That's the significance of having the g in front. And excuse me for misspeaking, all right? But hopefully that's clear, because that is an important difference. But again, that just comes back to just using exponents. And I know better, you know better, okay? So anyway, so that's the form of acceleration. Decaying to 0, initially g, all right? What about velocity? Well, velocity is the one that's going to decay to a constant. Because what happens is, look at the form here. We still have exponential decay. So this term is going to go to 0 as t grows, all right? So it goes to 0 as t goes to infinity. Okay, I don't know why I write asked, but as t goes to infinity. And so that means if this term is just going to go to 0, then we're just going to get vt, so terminal velocity times 1. Okay, so that means that for large values of time, then this is just, then vy just equals vt for large t. Okay? So that just means that the velocity approaches terminal velocity as time grows. Okay? So definitely that exponential function matches our expectations that an object in free fall speeds up for a while, and then it speeds up less and less and less and less until it eventually isn't speeding up anymore because it's reached that final speed that it's just going to maintain for the rest of free fall. And maybe until you open the parachute, right? Okay? And then finally, position is a bit harder to parse, but essentially it's telling us that the position function will eventually approach linearity, because eventually it's just going to approach vt times t, because at that point the vertical position is just going to be continuing to grow because you're still moving, but it's going to be moving at a constant velocity. So then eventually your function, your y function, it's going to be, so essentially it's going to be faster. So it's going to be, at first there isn't much at first there's a lot of acceleration, then it's going to decay to linearity. So it'll look like this. So if we have y and t, it's going to be like this until it eventually becomes linear, all right? And that's the final state is linear, because this is going to go to 0, and then we're just going to have, this linear expression, okay? Again, that's a little bit harder to think about, but the rest of the story is pretty clear, right? Acceleration decaying to 0, velocity decaying to terminal velocity, okay? And in this case, really it's the velocity actually isn't decaying. It has a decay function in it, but it's actually growing because it's 1 minus the decay function. So this initially says, what's the initial velocity? Well, it's 1 minus 1. Right? Because again, when t equals 0, e to the negative 0 is 1. So 1 minus 1 means that the initial velocity is 0. But of course it was, because this is for objects that start from rest. Okay? So all of these equations for Stokes drag are all for the condition of free fall objects that start from rest. Okay? Okay. Now, that's this is the meat of this section for sure. But there's also Newtonian drag. It just has the definition of Newtonian drag. Notice that's similar to the definition for Stokes drag. It has some coefficient. In this case, the coefficient is 1/2 d times rho times a, okay? And then, I'll say what those are in a second. And then notice here that it's proportional to v squared, okay? Now, we don't care how, what this is going to look like. We're not going to solve it in the same way because it's mathematically too complex. But what we do care about is what's d, rho, and a, okay? Well, d is the drag coefficient. It is entirely shape dependent. So different shapes have different values. They range between 0 and 1. All right. Rho is the fluid density. It's the density of whatever the object is moving through. So air, for example. So rho could be the density of air, which would be 1 kilogram per cubic meter. Okay. So it's the density of the surrounding fluid that is creating the drag in the first place. That's the rho. And A is the cross-sectional area of the object that's falling. The term for it is the plane form area. Essentially, it's the surface area that is being presented to the fluid that is creating the drag, okay? Or, causing the fluid to move around the object, and that creates the drag. And the actual mechanisms that are creating the drag, we're not going to get into them too much. We care more about just the consequences of the drag. Just like friction, right? We never talked about all the microscopic forces that create the friction in the first place. We just cared about the consequence of the friction. Because that's kind of where we're at in this semester of physics and mechanics. We're at the kind of the broad level. We haven't zoomed in on things like, electrostatic forces or something, okay? All right, so there we go, bird's eye view, looking at drag. But let's do that derivation, because so far I just told you to trust me that acceleration is decaying. But we can actually show definitively if that's the case, okay? So let's go. Right, so this is just our net force equation for an object that's experiencing drag. All right, simple as that. There's a gravitational force and there's a drag force. That's our free-falling object, but not really free-fall anymore because now there is a drag force, okay? So that's great, and that's going to be equal to ma. Okay, fair enough, right? This is just Newton's second law. Net force, there's two of them, and it's equal to ma, right? Here's where it gets interesting. Well, then I'm going to rewrite gravity as mg. We're going to rewrite the drag force as bv. We're not going to double count the negative, because again, this is just the negative just telling us the directionality, but I already accounted for that. And then we're going to set that equal to ma again. Then I'm going to rewrite a, something we haven't really done much, but I'm going to rewrite a as its derivative definition. It's dv over dt, isn't it? Right? It's the first time derivative of velocity. Okay. Then I'm going to take this, the b value, and I'm going to get rid of it so I can get v all by itself. So I'm going to divide all three of the terms, the two on the left and the one on the right, by b. Okay? And that's just going to make my life a little bit easier when I do the next step. Okay? So all I've done is just prep a little bit. Now what I'm going to do is actually move around the differential. So I'm going to multiply both sides by dt. Okay? When I do that, look what happens. Well, dt times dt over here, well, the dt in the denominator and the numerator cancel. So I'm just left with a dv, just a change in velocity, a differential velocity. Meanwhile, my dt shows up on the other side. Okay? Parenthetically multiplied by everything that was on the left side. Okay. Why would I do that? I would do that because now that is going to allow me to integrate. I'm going to integrate this side with reference to time, and I'm going to integrate this side with respect to velocity. Okay? So what is that going to look like? Well, like this. Okay? So first though, before I integrate, so got ahead of myself a bit, but before I integrate, I want to do something because we're going to see this again. Okay? And this technique is just that. It's a way to solve certain types of calculus problems. Maybe you've even seen it in the math class, but if you have, it's easy to forget it too. It's just one of many techniques. But here, I mean, the motivation is we just want to find acceleration, right? We just want to find the formula of acceleration, because we don't know it, right? And you can maybe trust me on it, but how do we show that? Okay, so I've got this idea that I have a dv and a dt, but here's the issue. If I go ahead and integrate this side, as I said that was the point of multiplying the differentials like this. Well, that's not great though, because I have a v over here, right? I want my v to be on the same side as my dv, because essentially this is v, this is the variable, and this is the differential. If I'm going to integrate them, they have to be together, right? Because it can't be an integral that doesn't have the right variable. So look what I do. I make sure that my differential and my variable are together, all right? And that means that everything in the parentheses is the long for the ride, okay? So then I end up with dv over this whole expression, mg over b minus v. Meanwhile, everything was on this side. I multiply it over to the dt side, and it just becomes the coefficient over mass, okay, times dt. And that's because there's no t in the expression, so I don't really have to worry about getting all my t's on the same side as my dt, because there simply isn't a t, okay? Now I'm ready to integrate, okay? So here we're going to do it. Now, I really like to do this with definite integrals with the actual variable in the integral, all right, in one of the limits, because I think that's a nice way of doing it in one step. It makes sense. You can obviously do it with constants of integration as well. I don't prefer it. I think that this is the way I will always show these types of examples, okay? So that means we're going to integrate from 0 to t. That's because we're assuming our initial time is 0 and our final time is the variable t, okay? All right. Meanwhile, we're going to integrate this side from 0 to the variable v, because again, we're assuming that our initial velocity is 0. And that's important, right? If I had an initial velocity that wasn't 0, I would have to change that lower limit, okay? All right, so let's do it. So here's the thing. When I integrate this side, it couldn't be more straightforward. We just pick up a t, all right? Because it's just constant. When you integrate a constant, it becomes linear. Now, what about this, okay? Well, this you have to know some rules about integration. Well, this whole thing is to the -1 power, okay? That's what being in the denominator means. Well, when I have some expression to the -1 power, that means when I integrate it, it becomes the natural log, right? All I'm saying is that x to the -1 dx equals the natural log of x, okay? All right, so that's cool. And that's what I have here, all right? And then I'm just going to evaluate it at the upper limit minus the lower limit. In this case, it matters that the lower limit is 0, because that means the lower limit doesn't just go away. If with linearity, it did, right? Because, m over b times 0 was just 0, so the lower limit doesn't show up. There's just one term. But here, when I when I evaluate the upper limit, okay, so I get this, the v just becomes a v because it's essentially my limit is the same as my variable, okay? Again, easy, but maybe cheaty, but easy, right? And then over here, when I evaluate the lower limit, well, that becomes 0, but then this term is still around. It's still now the natural log of that second term, okay? All right. And no chain rule necessary, by the way, because there was nothing on the v. The v was all by itself, which was why we did this step over here. Now you see the motivation. Okay? All right, so then we're going to clean this, this side of the equation, the right-hand side of the equation up, using the law of logarithms, because subtraction outside the logarithm is the same as division within the logarithm. All right, looks nice. All right, and then we're going to raise both sides to a power of e in order to get rid of the logarithm. All right, and that means that this over here is going to become a power of e. Ah, now you see where the exponential came from. And over here, it's just, well, we got rid of the logarithm, okay? And then we're going to put this right back over here and say that we're there. We actually made it. How so? Well, since vt is just by definition mb over g, which is just going to be this, which will cross multiply both sides by, all right, which is why that picks up in the front, and tau is m over b, well, we'll see, okay, well, look, there we have it. B over m is the same as t over tau. See where that comes from? They're the same. All right, and we just do a tiny bit of algebra, and we've got that expression. We did it. We found velocity. Now, of course, I said the point was to find acceleration. Well, actually, the best way to do it is just take the derivative of this, and derivatives are sure a lot easier than integrals. Take the derivative of this with respect to time, and you got yourself the acceleration. All right, so now we proved it. We proved using Newton's second law that these are the forms of velocity and acceleration for Stokes drag, for drag that is proportional to velocity, okay? Or at least other things we can pretend are Stokes drag. All right, so let's move on, all right? So now the thing about the types of examples here is they're either going to be really easy or fairly complex, because the easy ones are just going to use just kind of like the definition of terminal velocity, so really straightforward, just kind of like plug and chug problems, and the other ones are going to all involve exponentials, so they're inherently more complex, okay? So those are the two types. Problems that involve objects experiencing drag force at equilibrium, all right? When terminal velocity is reached, it could be either Stokes or Newtonian. And then type 2, complex problems that involve drag forces during the time-dependent acceleration. That's where we actually use the accelerations or the equations for decaying acceleration, for velocity approaching terminal velocity, and even the position one, okay? All right, so let's look at the simple ones first. Okay, so these are all ones in equilibrium. Example 1, marine snow consists of small organic and inorganic particles with an average mass of 1 milligram that sink to the bottom of the ocean. If the snow has a terminal velocity of 1 millimeter per second, right, very slow, then what is the Stokes drag coefficient B if we ignore any effect of buoyant force? And what is the time constant of this marine snow? All right, so here we're just going to use the definition of the terminal velocity for Stokes drag, mg over b. Then we're just going to solve for b based on the information we were given, because we were given everything except b. And there we go. That is our drag coefficient, 9.8 times 10 to the negative 3 kilograms per second. All right, and you can see the units, we arrive at the units here, naturally we see where they come from. All right, and then if we want to find tau, the time constant, okay, and this is just kind of getting familiarity with the terms really here. Well, that's just m over b, okay, and now that we know b, we can easily solve for it, and we could have found it differently, but here we go. There is our time constant, 1 times 10 to the negative 4 seconds, so a tenth of a millisecond, so very fast. So in other words, marine snow reaches its terminal velocity very quickly, so essentially it's in an equilibrium almost the whole time it sinks, okay? Let's look at another one. 2 identical asteroids enter the atmospheres of Earth and Venus. The rocks have plane form areas, given here as 8.4 times 10 to the negative 3 square meters, masses of 14.2 kilograms, drag coefficients of 0.4. All right, so they're fairly draggy, but not super draggy. Technical term there. If the density of Earth's upper atmosphere is taken as 0.11 kilograms per cubic meter, that's about the tenth of the density at sea level. And the density of Venus's atmosphere is 65 kilograms per cubic meter, because Venus has an incredibly dense atmosphere. Then how much faster will the terminal velocity of the asteroid be on Earth? Well, let's see. So for large and fast objects like asteroids, we're going to use Newtonian drag. And we were also given, some hints there that clearly we were given this information for a reason. All right. So then it's just a matter of solving for the difference between the terminal velocities. Earth's going to be the larger one. Why do we know Earth's going to be larger? Well, having a much larger rho means we're going to have a much lower terminal velocity for Venus. So that's kind of the giveaway. All right, we plug in all our numbers. Notice that here we have the acceleration of gravity on Earth. I looked up the acceleration of gravity on Venus. I didn't give it in the problem, but it's 8.87. You can easily look it up. And here's the drag coefficients we were given. They're shared by both. Here's the differing rho values for Earth and Venus respectively. Right? Notice again, rho is density, which is mass per volume, kilograms per cubic meter. Okay? All right, and then everything else is shared, and then we find out that the terminal velocity on Earth, with its thin upper atmosphere, is very fast, 868 meters per second, about almost 3 times the speed of sound. But on Venus, it's quite slow, 34 meters per second, like highway speeds. That's because that incredibly dense atmosphere means you can't fall very fast. And so the difference is huge. Things fall way faster in Earth's atmosphere than Venus's atmosphere, okay? Which, in terms of conservation of energy, means that they must burn up in Venus's atmosphere really, really readily, okay? All right, now let's finally do one that involves a little bit of actual non-steady state, non-equilibrium, okay? So, a large piece of oceanic crust is sinking in Earth's mantle underneath a continental plate. The piece of oceanic crust has a mass of, huge mass here, 2.2 billion kilograms and a terminal velocity of 1 meter per second. How long will it take for the crust piece to reach 90% of its terminal velocity? Okay, so this is, I would say, kind of the easier form of these problems where we actually have to deal with finding a velocity question, because we only have to concern ourselves with the velocity equation. Okay, so what we're going to do first of all is find tau. So I mentioned before that there's different ways to express tau. Like up here I express tau as m over b, but it's also terminal velocity over g, right? And you can refer back to the equation to see that that's obviously the case. And since we're given the terminal velocity and we know gravitational acceleration, we go ahead and find tau, 1/10 of a second, okay? So again, it's going to reach terminal velocity pretty quickly, but not quite as quickly as marine snow, all right? And so then we're just going to use our expression for time-dependent velocity, okay? So this is the velocity that is approaching terminal velocity and it's exponentially approaching it, okay? So I didn't show the graph on this one, but what this would look like if this was Vy and this was t, it would look like this. It would be approaching terminal velocity, and this is the value of terminal velocity. So it's like a horizontal asymptote, okay? All right, so then we're going to plug in. We know we want our final instantaneous velocity to be 90% of Vt, so I just plug that in. I leave Vt over there so they cancel out, and then it's just a matter of just solving for it, okay? So then I want to isolate and solve for t. How am I going to do that? Well, I do a little bit of algebra, add the exponential term to both sides, subtract 0.9 from both sides. This leaves me with a 0.1 because the 1 minus 0.9. All right, then I'm going to take the natural log of both sides. When I take the natural log of e, it's just 1. All right, so that's how I just get everything inside the exponent. They're inverse functions. Over here I have a natural log of 0.10 on that side. And then it's just a matter of isolating t. All right, and there we go, 0.23 seconds. Okay, so we found that it takes 0.23 seconds for the crust to reach 90% of its terminal speed. All right. Now again, it does asymptotically approach. So if I ask you for how long it takes it to reach 99.99%, it could be a very large number, right? But that's kind of impractical, right? Once you start, getting asymptotically close, because it will take ultimately an infinite amount of time. It never truly arrives there, because exponential decays never actually decay all the way, right? Okay. All right. Now let's do the couple of larger, more complex ones. Okay. So here we have a small objects like raindrops. So Stokes drag. All right, notice what I'm asking here. Okay, so first of all, I just remind you the form of the function. All right, I give you the drag coefficient. Okay, Stokes drag coefficient. Then I say, what is the velocity of this certain mass raindrop, because we do need the mass, that has been falling for 10 seconds. Okay, so then we're just going to use the expression for the time-dependent terminal velocity, the one that has the exponential in it. And then what fraction is this velocity of the raindrop's terminal speed? Okay, so that should be easy to compare. And then finally, how much time does it take the raindrop to fall 325 meters? This one's actually tough to solve for. I'll show you why. Okay. Now, also, I actually rederive everything here. I'll go through the rederivation. It's the same derivation that I showed you on the equation page, the key equations page. All right. Here is our free body diagram. Our two forces. I showed the direction of positive y. Our two forces, direction of positive y, and just the direction of acceleration. Okay. Non-constant acceleration, but it does always point down. Okay. So here we go. This is the magnitude of the drag force. Here is again the setup for the equation. All right, and then I'm just going to go ahead and work through it. All right, we're going to use the same definition of acceleration. Express it. Isolate our v and dv on the same side. All right, so it's slightly different, right? Because I wrote them at different times, so you can kind of see different approaches, but we'll arrive at the same place. Okay, so here we are. You can see same steps. We want the variable by itself for an easy antiderivative. That's why I've multiplied by the m over b. Okay, and here we actually set it up. Again, I'm using definite derivatives. I've always thought that was been the best way to do it. Okay, and then finally, all right, almost there, right, working through, doing the last steps. All right, and now we'll raise both sides to the power of e, because that will get rid of the natural log. And look, we're almost there. There we have it, right? There's our expression for the velocity. There it is, the final expression. Okay, the same one you have. Now notice here I didn't write t over tau. I left it as b over m times t. It's fine either way. I mean, I think that I'll do this because I know that I'm going to be given values of b over m. I might just leave it like this rather than calculating tau. maybe it looks a little bit more cluttered, but it's totally preference. You don't have to do it in terms of the time constant. Okay. Oh, here we go. And this this term exponentially decays with time. Okay, which means that of course terminal velocity is just going to approach this. All right, and because that's terminal velocity. All right. And so then we're just going to find it at 10 seconds because now that we have, and of course, since you already had it, you don't have to rederive it, right? But here, I did, right? But and then now we just evaluate it, and you could have done that with the problem. Just evaluate it at 10 seconds. All right, so that's all I do. Plug in our known values of m, g, b, and put t as 10. All right, and that gives me 89.8 meters per second. Okay. Well, then what fraction of terminal velocity is that? All right, here I'm also finding terminal velocity again. Right, as if we didn't know any of these equations, right? We're going in blind. Okay, so terminal velocity is 544. So this isn't quite there, right? That's the thing. It's with really low density air or relatively low density air, it takes a lot longer to reach terminal velocity than the examples that we looked at, in terms of like the sinking crust and the marine snow. So this one obviously is going to take a lot. Just 10 seconds is nowhere there, right? All right. So then the actual fraction is just 0.165 or about 16.5% of terminal velocity after 10 seconds. Okay. All right. And then for C, I'll remind you that for C, we were asking how much time does it take to cover a certain distance. Okay. Well, that's the one where we actually use the expression for vertical distance. And by the way, in order to get that expression for vertical distance, I haven't shown that to you, you would just integrate one more time. All right. So you'd integrate a second time. You take your velocity function, you integrate it. Okay. And when you do that, you get this. Notice here that this is, I'm using k instead of b. I'm sorry for that. Just it was a different version. I didn't realize. But here we actually plug in the numbers. So here's all the numbers. So you can clearly see that k is playing the same role as b. It's just a number to represent the coefficient. And now this is the part I say is actually difficult to solve because there's no way to actually isolate t because we have a t in the exponent and we have a t over here. At least algebraically there isn't. So the way you want to solve this is to do it graphically. All right, so maybe subtract 325 by both sides, graph this function in the graphing calculator and find the intercept, or just plug it into like a computer algebra system, like on a Texas Instrument or in Wolfram Alpha, and just ask it to solve for the variable t. And when you do that, all right, solve with a calculator or a computer, it's 8.34 seconds. Okay, so that's how long it takes to cover that particular distance. And that's actually quite interesting because it's nowhere close to linear yet because there's nowhere close to its final velocity. And so there's really no way to find this other than with, no way to get a reasonable estimate for how long it would take to cover that distance other than actually using this function that includes the exponential. Okay? All right, so now let's do our final example where we actually do have to do some calculus and it's not superfluous. Okay. All right, so we have a car. And I was playing around with different versions of this problem and I didn't realize when I actually finalized the notes that I forgot to specify the mass and the initial velocity. I should have, so here they are. They're supposed to be given in the problem. So a car with a mass of 1,220 kilograms turns off its motor traveling at 14.5 meters per second, so that's its initial velocity, and then it begins to roll to a stop with an approximation of Stokes Drag. Okay, and that's a rough approximation, but that means we can actually solve the problem. Okay, and we're taking the drag coefficient of this car, all right, as 25.5 kilograms per second. We're not using the Newtonian drag. Okay, the car is on level ground. How fast will the car be traveling after it has rolled 148 meters? This is fascinating, right? How do we do this? Okay, well, here's the thing. We actually have to go back and kind of define a new function because before our free body diagram included two forces, but here it only has one. This isn't actually drag with gravity. This is just drag. So that means that the exponential decay, we're still going to have an exponential decay. The acceleration is still going to exponentially decay to zero, but what's going to be the final velocity? The final velocity isn't going to be some terminal velocity because there's nothing to balance out the drag force. The final velocity will, of course, be zero. Okay, so let's see what happens. So here's our net force. All right, so we're going to use the definition of acceleration. All right, so we set it up. So it's easier in a sense. There's only two terms, so that's going to be nice. All right, so we're going to multiply both sides by dt, get our v on the same side as our dv. Then we're going to integrate. We're going to do indefinite integrals, so 0 to t. And v naught to v. Notice our lower limit is not 0 anymore because the initial velocity was not 0. Okay? All right, so then we're going to go ahead and evaluate both sides. All right, this one just becomes linear. And then we'll have the natural log of v minus the natural log of v naught. All right? Okay? And then we'll use our law of logarithms, so a lot of the same steps. And then here we go. We have our velocity function. Okay? Now, this is also going to be nice because now you're going to see what it looks like to find a position function. All right, we're going to integrate again for a position function. And this is the same thing that you would do to get the equation that is given in the key terms, okay? all right, or key equations. So we're going to get, right, we were just going to represent v as dx over dt. That's all I've done is just write v equals dx over dt, okay, by definition. And then I multiply both sides by dt. Why did I do that? Well, now I have everything that is a function of t on the same side as the dt, and I've got the dx by itself because there is no x in the equation, okay? So then I'm going to go ahead and integrate both sides. Definite integrals, 0 to x and 0 to t, okay? All right, and here, both the lower limits are 0 now because time starts at 0 and position starts at 0. All right, and look what happens, all right? I'm just going to evaluate that integral, and here we go, all right? And notice here I evaluated the upper and lower limit, all right? And so that's where you're going to get that 1 from. And notice that 1 also shows up in the other expression because when you evaluate e to the power of 0, you naturally get a 1. Okay, so there you go. Here's our final expression for position. All right, and this one's nice because unlike the other one, there's no extra t. All right, and that means that this one actually can be solved directly rather than graphing it. All right, so then we're going to find t for x equals 148 meters. All right, so then I'm just going to do some algebra to isolate t. All right, so basically I'm just undoing the exponent with a natural log, and I eventually then solve for t. All right, plugging in our values, plugging in our mass, plugging in our drag coefficient, plugging in our initial velocity. Okay, all right, so let's do it. 11.5 seconds. Okay, so it takes 11.5 seconds for this car experiencing, decaying velocity, okay, exponentially decaying velocity to cover 148 meters. Okay, so then how fast is it going? Well, now we just take that time and plug it back into this function, okay, which of course was the intermediate step to get to our position function, but now is also going to be useful to answer the question. All right, so then use this time to find final velocity. There's our function. Plug in our 11 seconds, drag coefficient, mass, initial velocity. There we go, 11.4 meters per second. So I think that's pretty cool. Like, this is really showing what you can do with this idea, with this definition of the drag force, whether it's combined with gravity or not. Okay? All right, so that's it for lecture 6, introducing another thing we can do with Newton's laws, a whole nother type of interaction between kinematics. I hope it's been interesting. I hope it's been informative. Thank you so much for watching.